In this video, we solve problems 1, 2, and 3 from Differential Equations, quiz number 6 for the 2021 semester, spring 2021 semester. There were multiple versions of this quiz. This is version A. Problems 1, 2, and 3 cover standard L24, which is about the definition of the Laplace transform. So in the first problem, you're given a piecewise function, and you'll just use the definition to find the Laplace transformation of that function. And for the other two questions, you're asked to use the table of Laplace transforms to find the appropriate transform, or use the table of Laplace transforms in partial fraction decomposition to find the appropriate inverse transformation. So that's the plan. Let's get started. On problem number 1, we're given a piecewise function f of t equals this, and we're asked to use the definition of the Laplace transformation to find the Laplace transformation of f of t, which we'll call f of s. Since we're asked to use the definition, rather than using the Heaviside function, we have to evaluate an improper integral. So let's start by stating the definition of the Laplace transform, or the Laplace transformation operator. So by definition, the Laplace transform of f of t is the integral from 0 to infinity of e to the negative st times f of t dt. Now we've got a piecewise function here, so we're actually going to evaluate this integral by evaluating two different integrals and then adding them together, because the function f of t is defined to be this function on the interval from 0 to 3, and then this function on the interval from 3 to infinity. So while it's not required, I recommend that you graph it just so that you can visualize what's going on. This is optional. Now f of t is e to the negative t, so that's a decaying exponential function on the interval from 0 to 3. So at t equals 0, we'll have e to the opposite of 0, which is just e to the 0, which is 1. And when t equals 3, we'll have e to the negative 3, which is very small, and there will be an open circle there. And so it would continue and it would approach that x-axis as an asymptote. It would look like this if it went on to infinity, but we're just talking about that exponential function on the interval from 0 to 3. So that's our first piece. This is not to scale and it's not perfect, obviously. E to the negative 3 is actually very, very small. But this gives us an idea of what's happening. And then over here, on the interval from 3 to infinity, we have a piecewise linear function. And when t is equal to 3, our y value for this function is 1 minus 3. So that's going to be 1 minus 3, which is negative 2. And then it has a slope of negative 1. So we would go to the right 1 unit and then down 1 unit. And we would see that. So that is our f of t. So I think you can see just from this picture that you'll have to split that improper integral into two pieces. One piece on the interval from 0 to 3. And then another piece on the interval from 3 to infinity. And we'll add those together. And I've left spaces here for my f of t on this interval and my f of t on this interval. On this interval, my f of t was e to the negative t. And on this interval, my f of t was 1 minus t. So we'll write the Laplace transform of f as a sum of two integrals. And then we'll just evaluate those integrals. Now for the integral on the left here, it's helpful to use this fact from algebra. If you have x to some power times x to a different power, you just add the exponents. That's the same if we're dealing with exponential functions rather than power functions. If the bases are the same, you can add the exponents. Here, our bases are the same, so we can add the exponents. And I want to factor out a -1 and factor out a t as well. So we'll have that right there. And that can be evaluated pretty easily. Remember from calculus 1 or calculus 2 that the antiderivative of e to the kx is e to the kx times 1 over k plus c. Now remember where that 1 over k comes from. If we're taking the derivative of e to some power, we get e to that power times the derivative of the inside. So I'd multiply by k if I were taking the derivative. Since I'm taking the antiderivative, I divide by k. So in this case, our k is the negative quantity s plus 1. So what we'll have here is e to the negative quantity s plus 1 times t divided by our k, or multiplied by 1 over the k, that's fine. And we evaluate this on the interval, or evaluate this from t equals 0 to t equals 3. At t equals 3, we'll have e to the negative 3 times the quantity s plus 1 over negative s plus 1. And at t equals 0, this will be e to the 0. So I'll be subtracting a negative e to the 0, which is 1 over s plus 1. So we're going to add 1 over s plus 1 there. Okay, so that's the first piece, that first integral. Now, the second part is more involved because we have that infinite upper limit. So that makes this integral an improper integral. If we want to evaluate an improper integral, the first thing that we need to do is we need to write it as the limit of a proper integral. Because all improper integrals are just limits of proper integrals. So we say when we're finding this, what we really mean is we want to find the limit as b goes to infinity of this proper integral. And I'll put my polynomial first because I like to have my polynomials first. So this is representing, or one thing this could represent is an area under the curve. If t is just some parameter from t equals 3 to t equals b. We can find that area in terms of b as a function of b so that we could plug in b equals 10, b equals 100, b equals 1,000,000. And those would all give us the right area under the curve. And then we're going to say to ourselves, okay, well, what happens to that quantity as b goes off to the far right, as b goes to infinity? So that's the plan. In order to do that, we should use integration by parts. This is the integral of u times dv. I've got a polynomial times an exponential. Since it's a polynomial times an exponential, I would recommend using tabular integration here. So we take the derivative twice, and then we take the antiderivative here. Using that kx rule again, we're going to divide by the k. So we're dividing by negative s, or multiplying by negative 1 over s, same thing every time we take an antiderivative. And then because of the integration by parts formula, which comes from the product rule, we'll have this quantity times positive 1 plus this quantity times negative 1 plus c as our antiderivative. So our f of s is equal to this. We've got negative e to the negative 3 times the quantity s plus 1 over s plus 1. I just brought that negative up to the numerator or off to the left-hand side. That's fine. And then over here, we have the limit as b goes to infinity of this expression. So I think I will factor out the negative 1 over s there. So I've got negative 1 over s times 1 minus t times the exponential minus a negative 1. So it's going to be plus 1 over s squared times the exponential. And we evaluate that from t equals 3 to t equals b. And I see that I've got an exponential in common here and here, so I will factor that out as well when I evaluate at b. So when I substitute in t equals b, I'll have negative 1 over s times 1 minus b, factoring out the exponential, plus 1 over s squared. All of that is times e to the negative s times b, because we're replacing t with b. And then when we replace t with 3, we'll have 1 minus 3 is -2. -2 times -1 over s is going to be +2 over s plus the 1 over s squared times e to the -3s. And we're evaluating the limit of all of that as b goes to infinity. But there's no b in this piece. That should be an s squared, sorry. There's no b in this piece, so that's constant. So we can just bring that constant out because the limit of a constant is just the constant. Okay, now this piece, as b goes to infinity, if s is negative, or if s, well, let's see, if s is 0, this is just 1. And if this is 1, well, if s is 0, this wouldn't be defined anyway, so s can't be 0. So let's say s is not 0. If s is negative, this negative number times this -1 is going to be a positive number, and b is going to infinity. So b is a very large positive number, or we should think of it that way as we're computing this limit. So this would be a negative times a negative, which would be a positive times a positive would be a positive. As b goes to infinity, this would go to infinity if s is negative. But if s is positive, this is e to a large negative power. The absolute value of the number is very large, but it's going to be negative. So this would go to 0 in that case if s is positive. And as b goes to infinity, this factor goes to negative infinity, and then we multiply by -1 over s. So that's going to go to positive infinity. So this is an infinity times 0 indeterminate form under the conditions when it actually has a chance of converging, which is when s is strictly positive. So I need to use L'Hopital's rule. I need to rewrite that and use L'Hopital's rule in order to compute that limit. So I will put this negative, or e to the negative s times b. I'm going to write it as 1 over e to the sb and then put that in the denominator. So we'll have this. And now this is an infinity over infinity indeterminate form, and we can use L'Hopital's rule. Okay, so by L'Hopital's rule, this limit is equal to the limit as b goes to infinity of the derivative of the numerator with respect to b, treating s as a constant. So of -1 times the -1 over s, which is going to be +1 over s, over the derivative of e to the sb with respect to b. So that's going to be e to the sb times the derivative of the inside with respect to b. That's a constant times b, so we'll just have that constant. And as b goes to infinity, this is a constant over something that's very large, assuming that s is positive, because we've already assumed that. If s is positive and b is positive and b is going to infinity, this is going to be a constant over something very large. So this fraction will be very small. It's going to go to 0. And f of s is equal to this expression right here. So it's equal to this plus 0, but that's the same as just that. Okay, so what did we do? We wrote the improper integral as the limit of a proper integral. Then we evaluated the proper integral. Using the fundamental theorem of calculus. And then finally, we evaluated the limit, and that required us to use L'Hopital's rule. And that is how we solved problem 1. Now with problem 2, we're just asked to use the table of Laplace transforms in order to compute some Laplace transforms. So here's our first one. We have f of t equals this. Now remember, the Laplace transformation is a linear operator. So that just means we can take the inverse, or excuse me, the Laplace transform of each of these pieces separately, and we can factor out any constants that are multiplying our functions. So I can think of this as a constant times t cubed and a constant times t to the second power. So we've got a rule for t to the n and its Laplace transform. So we'll use that here. This constant that's just by itself, we can think of that as a multiple of 1. And we have a Laplace transform for 1. And then we've got a sine of 5t and a constant times cosine of 2t. So it looks like we need the rules for t to some power, for 1, and sine and cosine functions. So let's look at our table of transforms and find the appropriate entries in our table. So this is the table of Laplace transforms that you will have access to during your quizzes. We have the 7 here, so we're going to need the Laplace transform of 1. So that's entry number 1 in our table. It says the Laplace transform of 1 is just 1 over s. And I've got t to some power here and here, so entry number 3 will work for that. The Laplace transform of t to the n turns out to be n factorial over s to the n plus 1. So that'll take care of these two guys. And I've got a sine and a cosine of a constant times t for both of those. So I'll just keep scrolling down, looking for a sine or cosine. Oh, there they are, number 7 and number 8. So entry 7 tells us that the Laplace transform of sine of kt is k over s squared plus k squared. And entry number 8 tells us that the Laplace transform of the cosine of kt looks just like the sine, but it has an s in the numerator. Okay, so that's exactly what we need. These 4 are what we need in order to compute this transform. So let's compute it. Let's do it. So first we'll say the Laplace transform of f is this. Now bring your constant down, and then we're going to do some pattern matching. So we look over here at these 4 entries, and I see t to some power. That's entry number 3, t to the n. So with pattern matching, our n is equal to 3, just matching that pattern to that pattern. If n is equal to 3, what we get is a 3 factorial over s to the 3 plus 1, and 3 plus 1 is 4. So we have that 4 times the Laplace transform of the t to the third, which is this. Then we bring the 3 down, the negative 3 down, and we match the pattern again. We've got t squared, and that means our n is going to be equal to 2. According to this rule, we get 2 factorial over s to the 2 plus 1. 2 plus 1 is, of course, 3. Bring your 7 down. It's going to be 7 times the Laplace transform of 1, which is 1 over s. And for the sine and cosine, we need to use these 2. Now notice that our entry in our table says sine of kt. So this is sine of 5t, so we need to identify k. The number multiplying t is our k, so that's our 5. K is 5. And according to our rule, the Laplace transform of sine of kt is k, which is 5, over s squared plus 5 squared, and 5 squared is 25. On this last one, you want to bring the negative 2 down. Got cosine of 2t, matching the same type of pattern, cosine of kt with the cosine of 2t, k equals 2. And for that one, we get an s over s squared plus k squared. K is 2, k squared is 4. So that is our answer. It's just not simplified. Let's simplify it. If you want, you can write these numbers, these coefficients as themselves over 1, multiply straight across. 3 factorial is 3 times 2. 3 times 2 times 1, which is 6. 6 times 4 is 24. So we've got 24 over s to the 4th here, minus 3 times 2, which is 6 over s cubed, plus 7 over s, plus 5 over s squared, plus 25. And then over here, we'll distribute the negative 2. So we have negative 2s over s squared plus 4. And that is how we handled that. Okay, great. And let's look at part B now. Okay, so we have an exponential this time and a hyperbolic sine function and a hyperbolic cosine function. So let's find those entries in our table. All right, it looks like entries 11, 12, and 13 are exactly what we need. Entry number 11 tells us that the Laplace transform of e to the at is 1 over s minus a. We derived that in class. And entry number 12 tells us that the Laplace transform of hyperbolic sine of kt is k over s squared minus k squared. And entry number 13 tells us that the Laplace transform of hyperbolic cosine of kt is s over s squared minus k squared. So we're just going to apply those individually here, here, and here. So the Laplace transform of g of t is 5 times the Laplace transform of e to the at. Matching that pattern, the number multiplying the t here is a negative 1/2. So we have 1 over s minus a negative 1/2, so that's s plus 1/2 times our 5. And we'll bring the negative 4 down, and this is hyperbolic sine of kt, where k is the number multiplying the t, so k is 2. So we're going to get 2 over s squared minus k squared. If k is 2, k squared is 4. Then we bring the 2 down, and we have hyperbolic cosine of 5t. So k is 5 in this case, and the Laplace transform is s over s squared minus 5 squared, which is 25. So that's our answer, it's just not simplified. We'll write each of those integers as themselves over 1, and then multiply straight across. Now on this one, I might also simplify because I don't like having that 1/2 in the denominator. And to clear the fractions, you might multiply by 2 over 2. So we would have 10 over 2 times s is 2s, plus 2 times 1/2, which is 1, minus 8 over s squared minus 4, plus 2s over s squared minus 25. And that's that. Now, the last problem for this introductory standard involves computing an inverse Laplace transformation of a rational function in S. So we notice right away that we've got a third degree polynomial in the denominator, and we don't have any third degree polynomials in our denominators for our table of Laplace transforms. So we have to rewrite this using partial fraction decomposition. And that requires factoring that denominator first as much as possible. And then once it's factored, then we can find the appropriate form of the partial fraction decomposition, and then we can find the values of the constants that are necessary in the numerator to cause the decomposed version to equal the original fraction. So we'll start with our s cubed minus s squared plus s minus 1. Now, this doesn't always work, but this time it will work to use what's called factoring by grouping. If I group these two guys together and I group these two guys together and I factor out everything these two have in common and I factor out something from here, it turns out I'm going to have a common factor. Now, if you're saying, how did you know that? It's because I just did that process in my head and I noticed that I do have a common factor after doing that here and here. So let me show you what I mean. We group the first two together and the second two together. And then we look at these two guys and we say, what do they have in common? Well, they have an s squared in common. So let's factor that out. And then we say to ourselves, s squared times what will give us s cubed? That's an s. S squared times what will give us the negative s squared? That's a 1. And so I've got this as the factored form of this. And over here, I want to factor something out as well. Well, this already has an s minus 1 in it, and that's what I want it to have something in common with this, so it already has an s minus 1 in common. So I need to factor out something from this. I'll factor out a 1, which doesn't really feel like factoring anything, but it'll make it easier to see what the next step ought to be. So after you factor this group and this group as much as possible, and that's why we call it factoring by grouping, then you look at this expression and this expression, and you say to yourself, what do those have in common? Well, they both have a factor of s minus 1. So you can take the s minus 1 factor out. And then you say to yourself, s minus 1 times what will give you this first group? Well, an s squared. And s minus 1 times what will give you the second one? Well, that's a plus 1. So you have s minus 1 times s squared plus 1 in that denominator, and s squared plus 1 is an irreducible quadratic. So this is our original fraction with our factored denominator. Now, once you've done that, you want to write this in the appropriate form for its partial fraction decomposition. Okay, so we'll write down the partial fraction decomposition, or write down the form of the partial fraction decomposition for f of s. Okay, so we have 1 plus 2s minus s squared over s minus 1 times the quantity s squared plus 1. Well, that is a linear factor. It's not repeated, so we'll have a constant over that factor here, and then we'll add the appropriate term for this irreducible quadratic factor. So we'll have b times s plus c in the numerator over that guy. Then we'll take this and we'll multiply by s minus 1 times s squared plus 1. We'll simplify as much as possible. These guys reduce, and these guys reduce. These guys reduce, and these guys reduce. The LCD is always the original denominator. Okay, and the original numerator is still there. And then we'll have a times the quantity s squared plus 1 plus bs plus c times the s minus 1. And then from here, you usually just choose s values that will cause the factors to be 0. But since we have an irreducible quadratic factor and just a single linear factor, there's only one s value where that will work, and it's the s value that will cause the linear factor to be 0. When s equals 1, s minus 1 is 0. So we'll substitute s equals 1 into both sides. We'll have 1 plus 2 minus 1, so it's going to be 3 minus 1, which is 2, equals a times s squared plus 1. So it's going to be 1 squared plus 1. 1 squared is 1, so 1 plus 1 is 2. And when s is equal to 1, we're going to have something times 0, so that part is 0. So we have 2a is equal to 2, so a must equal 1. If you want, you can divide both sides by 2, and you get a equals 1. Now you've still got two constants you need to solve for. You need to find a b and a c. If to find those two constants, you just choose two different values of s to substitute in here. And I just choose values of s that are simple to evaluate the expression at. So we've already chosen s equals 1. I'll choose s equals 0 next, and maybe s equals -1 for the one after that. So with those two extra values of s, that's going to give us two equations and two unknowns involving b and c. With those two equations and two unknowns, we'll be able to find b and c. Excuse me, so let's do that on the next page. We have 1 plus 2s minus s squared times the quantity, or equals a times the quantity s squared plus 1 plus bs plus c times s minus 1. Okay, and if we evaluate all of this at s equals 0, we've got a 1 on the left-hand side, and that will equal a times 1, which is just a, plus, if s is 0, we'll have b times 0 plus c, which is c, times 0 minus 1, which is -1. So this tells us that a minus c equals 1, but we already have a. We found a last time. A was equal to 1 here. So that's nice. We know what a is. And if we subtract 1 from both sides, we get 0 equals the opposite of c. So c must be the opposite of 0, which is 0. Very nice. We need another value of s. So let's try s equals -1. We'll have 1 plus 2 times -1 minus -1 squared equals a times -1 squared, which is 1. 1 plus 1 is 2. Plus b times -1 plus c, all of that times the quantity, -1 minus 1, which is -2. So this ends up being 1 minus 2 and this is 1, and we're subtracting it, so it's a -1. So we have that. I'll distribute the -2 here as well, so that'll give me a positive 2b minus 2c. And I end up with this. If you want, you could divide everything by 2. But we already know what a and c are. We know that c is 0, so we can substitute that in. And a was 1, so we can substitute that in. So we'll subtract 1 from both sides, and we get b equals -2. All right, so that means f of s is actually a over s minus 1 plus bs plus c over s squared plus 1. And our a value was 1, and our b was -2, and our c was 0. So that's actually really nice and easy. I'll factor out that -2 so that looks more like our rules for inverse transforms. Okay, so that's f of s. Now, the whole point of that partial fraction decomposition was to be able to take the inverse transform of these guys. So if we're looking at our table, we're going to use a lot of the same entries that we used before, but we're using it backwards. Instead of going from the left column to the right column, we're going from the right column to the left column. So we're in the right column, and we're looking for 1 over s minus 1. Well, that's our e to the at rule. It's just in reverse. So I'm going to use entry number 11, but instead of going from the left to the right, because I'm taking an inverse Laplace transform, I'm going to go from the right to the left. So I'll be using that rule with a equals 1, matching the pattern. And here I've got an s over s squared plus 1. That looks like number 8. So that's a cosine function. We go backwards. And k squared in this case is 1, so k would equal 1. Okay, so what I'm using here again is going from the second column, that right column, to the left column. And taking the inverse transform that way. The inverse transform of 1 over s minus a is e to the at. If a is 1, it's going to be an e to the t. Then I'll bring my -2 down because the inverse Laplace transform, or inverse Laplace transformation, is a linear operator, just like the Laplace transform is a linear operator. And I'll multiply by cosine of kt, where k equals 1. So that's just cosine of t. So that's our f of t. That is the function that we would take the Laplace transform of. After getting a common denominator here and simplifying, we would end up over here. The Laplace transform of this is this, common denominator, and simplification gives us this. And so the inverse transform of this guy is this guy. That is the end of our video covering standard L24. I'll see you in the next video to discuss standard, or the quiz problems from standard L25.